So the concept of formal charges will help you to determine what structure is the most likely possibility for the actual structure of a compound. So to calculate your formal charge, you need to take the number of valence electrons minus the number of lone pair electrons minus the number of bonding electrons divided by 2. Lots of words, pretty simple formula when you see where this all comes from. So this is used to determine the most likely Lewis structure. And so the goal, there are a couple goals when you're looking at formal charges. First of all, a formal charge must, how do I want to say this? The total formal charge of a compound, the total formal charge for a compound must equal the actual charge of the compound. So for a covalent compound, that will be, you need the total charge of it to be 0. If it's a polyatomic, so like hydroxide has that -1 charge to it, so then the formal charge must also equal -1. Does that make sense? The total formal charge. So what I mean by that is that every element or every atom in the compound will have a formal charge associated with it. And so when you add all of the formal charges together, it either needs to be 0 or the charge of the polyatomic. So an example, let's practice this. But yeah, this one will work. So if we start with CH4, we kind of assume that the drawing or the Lewis structure will be carbon as the central atom because it has the lowest electronegativity. And so drawing it this way, we complete the octets or the duets for hydrogen. And we know that we have 4 valence electrons from carbon and then 1 per each of the 4 hydrogens for 4. So we would have a total of 8 valence electrons to work with, which we have drawn out. So far, this structure, this Lewis diagram looks legit. All of our rules have been met. But now we also need to check that our formal charges also meet the requirements. So if we look at carbon, the central atom here, we know that carbon, when we're talking formal charges, we need to look at the number of valence electrons carbon brings to the table. So how many valence electrons does carbon have? 4. Okay? Then we need to look at the number of lone pair electrons. So on this carbon atom, are there any lone pair electrons? No, they're all bonded, right? So there are no lone pairs. So then the next part is you take the number of bonding electrons. So how many electrons are involved in the bonds? 8. 1, 2, 3, 4, 5, 6, 7, 8. And then you divide it by 2. So this really would be 4. So 4 minus 0 minus 4 equals 0. So that means that your formal charge on carbon is 0, which is good. We want as many of our formal charges to be near 0 or actually 0 on the dot as we can get. All right, so then if we look at this hydrogen right here, because I said every atom involved in the compound needs its formal charge figured out. So this hydrogen brings how many valence electrons to the table? 1. okay? Minus, how many lone pair electrons are there? 0. Minus the number of bonding electrons divided by 2. So how many bonding electrons do we have here? 2. So we'd have 1 minus 0 minus 1 equaling 0. Okay? So we can go through and figure out the formal charges on all of these hydrogens, but they all have the same bonding situation as that purple one, correct? Yeah. So we can make the assumption that they're all going to have the same formal charge as that first hydrogen. And so since all 5 elements or all 5 atoms on this have a formal charge of 0, we know that the best structure for this compound is in fact what we had originally drawn. Does that make sense? So we check off, it follows our octet rule, it follows the required number of valence electrons, and we have our best case formal charge scenario represented. Okay? So when we look at, I believe this CLO3 was practice problem 3 from your assignment. So when we look at this, we need to first figure out how many valence electrons we need in this compound. All right, so how many electrons come from chlorine? 7. 1 times the 7. Plus, how many comes from the 3 oxygen? 6. And how many come from this charge here? 1. So 7 plus 18 plus 1 is equals 26. So we know we need 26 valence electrons. So in this case, chlorine is the least electronegative atom. So replace the oxygens around it. And to complete chlorine's octet, we'll throw another 2 up there. And then we need to fill in around the oxygens in order to satisfy our octet rule. Once we have done that, we should probably just verify that we have the correct number of electrons placed. We've verified that the octet rule is happy. So now if we count our electrons, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. So this could be a viable structure for the chlorate ion. But our last verification is we need to check the formal charges. So we do that. You can start with the chlorine. How many valence electrons does chlorine have? 7. Then how many lone pairs electrons are on chlorine? 2. Those right here. So there's 2 unpaired or unbonded electrons minus your number of bonding electrons divided by 2. 6. So we have 6 bonding electrons. Those would be 2, 4, 6. So then we'd have 7 minus 2 minus 3 gives us a positive 2. So that tells us that our formal charge on the chlorine is positive 2. So that's not ideal because what is our target formal charge? 0. But even just that, we should probably just know something's wonky and we should reevaluate. So when it comes to this reevaluation, we are going to be moving electron pairs. And so when we do that, we have to look at, are any of these elements present? Are they able to expand their octet at all? It's either chlorine or oxygen able to expand their octet? Yeah. Yes. And which one can? Chlorine. Because chlorine is in the third period, and elements in the third period have the ability to have an expanded octet. That was part of yesterday. Yep. So what we can do is we can take a pair of unbonded electrons from an oxygen, and you can pull them from either of the oxygen atoms. It doesn't matter. So I'm going to take this pair and scoot it into here and form a double bond. Okay? So if we do that, what is our new formal charge? We still have 7 valence electrons on chlorine, and we still have 2 lone electrons. But now, how many do we have involved in the bonds? We have 8. So 8 divided by the 2 is 4. And what is our formal charge here? It would be positive 1, right? Okay, so that was good. But we should also check if that is good for this oxygen. I mean, if this oxygen has some crazy formal charge now, we should make sure that that didn't totally screw up the oxygen. So looking at that oxygen's formal charge, oxygen generally has 6 valence electrons. Does it have, how many unbonded does it have? 4. Involved in the bond, how many are there? In this bond right here, we have 4. So here we have 6 minus 4 minus 2 for a formal charge of what? 0. This is great. We like it when the formal charges are 0. What would be, we should probably, I guess, check the formal charge of this oxygen to see what the formal charge is when there's no double bond. So that would be 6. We have now 6 unbonded, and our, minus, we have 2 divided by 2 in the bond. So we would have 6 minus 6 is 0, minus 1 is a negative 1 charge. So that's not ideal. So how should we fix this oxygen? Take an unpaired and make it a double bond. Good. So we'll take this pair and make it a double bond. Oops. So that goes away. So now on this oxygen, what is its formal charge? 0. On the first oxygen that we manipulated, what is this formal charge? 0. We said that chlorine's formal charge was, it was plus 1, but did that change now? Yeah. Yep, now that that's changed, we now have 10 bonding pairs. Is that correct? Yes. 10 divided by 2 is 5. So now our formal charge on chlorine is 0. This is sounding good. What is our formal charge, though, on this oxygen? We haven't changed anything. So if we haven't changed anything, what's our formal charge on oxygen? Negative 1. So what is the overall formal charge currently of this chlorate ion? Negative 1. What overall formal charge do we want? 0. Negative 1 or 0? Negative 1. Why do we want a negative 1 charge on this ion? Because that was the charge on the ion originally. So we have to have a negative 1 charge. So our best diagram is not the nice simple one where we complete our octet, we have our correct number of valence electrons. We actually have to break the octet rule on chlorine so that we can get the formal charges to 0, which gets us to our -1. So the most appropriate diagram for this compound is actually this. Now, the hiccup with this, we should actually put it in brackets first and put the -1 because it is a polyatomic. That's just the polyatomic rule. However, who's not to say we didn't make a double bond here but not here? Is there a rule that said we had to start with the oxygen on the right-hand side? No. So what that means is that this structure is actually a resonance structure. And so what has to happen is you, or who's ever doing the problem, needs to indicate that this single bond can actually either be in this place, it could be here, or it could be here. And that doesn't matter which one it is in, but you have to represent that it's possibility that it could be in either one of those 3 locations. So to do that, you draw arrow, a double-headed arrow, and you redraw your compound with that single bond in each of the 3 possible locations. Oops, oh. So not only did you have to change the structure based on the formal charge information you gathered, you also had to account for the different possible locations for that single bond.